These suspects are all white people, shooting other white people. Yet I can't remember how many times I've seen Apu get shot. This could be tested in the real world. I wonder if minority status would affect being a victim of crime. Clearly, the producers seem to think that whoever shot Mr. Burns is a non-visible minority. Calling stats group! Guys, I have a perfect question for our video. Who shot Mr. Burns? It's perfect. We can see if visible minority status affects crime victimization. Mr. Burns is a white guy who got shot, and all the suspects were white. But Apu gets shot, all the time, by a white guy. So what does visible minority status have to do with being a victim?
The chi-square test is the most frequently used test within the social sciences, as it can be conducted with variables at any level, due to the fact that it is a non-parametric or distribution-free test, but it is most appropriate for nominal level variables. The Helium-Proust textbook defines the chi-square test as a non-parametric test of hypothesis for variables that have been organized into a bivariate table. The chi-square tests for independence, which refers to the relationship between the variables. They are independent if the classification of a case into a particular category of one variable has no effect on the probability that the case will fall into any particular category of the second variable. A null hypothesis is needed and always states that the variables are independent. If the null hypothesis is true, then there will be a difference between the frequencies expected and the frequencies observed. If the null hypothesis is false, there will be a large difference between these values. There are several limitations to this test, such as firstly, it is difficult to interpret the data when there are many categories. 4 or fewer scores generally work best. Secondly, small samples cause a problem when cells have a frequency of 5 or less, as it can no longer be assumed that the sampling distribution of all possible sample outcomes is accurately described. When this is the case, we use the Yates correction for continuity. The formula for this is x squared corrected equals the sum of absolute values of the difference between the observed and expected frequencies for each cell minus 0.5 squared over f expected. Absolute values ignore positive or negative signs. Thirdly, when the sample size is too large, we might declare relatively trivial relationships to be significant, as the probability of rejecting the null hypothesis increases as the chi-square test is sensitive to sample sizes. It is also limited in the sense that the tests do tell us whether or not the results are statistically significant, but does not tell us whether they are important in any other sense. Measures of association, which will be learned later in the term, are better suited for discussing this importance.
To begin the process of chi-square testing, one must make a bivariate table. The variables that we are using are criminal victimization and visible minority status from the 2009 General Social Survey. The bivariate table is composed of rows and columns which intersect to form cells. The independent variable is placed in the columns and the dependent in the rows. The data is placed into the columns and marginals or subtotals for the columns and rows are added. Concise labeling is important.
We use this bivariate table to create the computational table, which will help us gain the x-square obtained value, which is needed to complete the chi-square test. This is done through taking the totals for each cell, known as the frequency obtained, and using them to find the frequency expected. This is calculated through taking the marginal for the row and multiplying it by the marginal for the column, and then dividing by n. This is done for each frequency obtained, giving us the frequency expected column. Both of these columns should equal n, which is the total number of cases. It is a quick way to test that the math has been done correctly. For the next column, we then subtract the frequency expected from the frequency obtained, and then this is done for each value. When all the values in this column are added, the total should always be 0. We then take the value from frequency obtained and subtract it from frequency expected and then square it. These values should all be the same. To complete the computational table and find x-square obtained, we then take the squared values from the previous table and divide them by the frequency expected for that row. These values are then added together to get the x-square obtained. There is a formula for all of this that will be explained in later steps. Step 1 is where we make assumptions and see if our variables will meet test requirements. To start, we need to make sure that our variables are acquired through an independent random sample. The data being used was from the 2009 General Social Survey, meaning that this requirement is fulfilled as we know that every person in Canada has the opportunity to fill this out. Secondly, although the CHI test can be used for all levels of measurement, it is best suited to nominal level variables, which is what both of our variables are. Thus, both requirements are met and we can move forward with the CHI test.
Step 2 is where we state our null hypothesis. For chi-square test, the null hypothesis states that the two variables are independent from each other. Thus, for our test, our null hypothesis would be that there is no relationship between criminal victimization and visible minority status, meaning that our research hypothesis is that there is a relationship between the two.
Step 3. Selecting the sampling distribution and establishing the critical region. For chi-square tests, an x-squared distribution is used, which is associated with the variables found in Appendix C of the Healy-Proust textbook. The sampling distribution of sample chi-squares is positively skewed, meaning that for the chi-square test, the critical region is in the upper tail. We also need to establish the degrees of freedom to complete this test. For a 2x2 table, the degree of freedom is automatically 1, regardless of the number of cases in the sample. When the table is larger than 2 by 2, we gain the degrees of freedom through the formula df equals r minus 1 times c minus 1, which means that the degree of freedom is the row subtract 1 multiplied by the column subtract 1. An alpha level also needs to be established. For this test, we chose to set ours at 0.05, a typical alpha level within the social sciences. Using Appendix C, we can establish our x-squared critical value by matching our alpha level with our degrees of freedom. In this case, our x-squared critical level is 3.841, meaning that our null hypothesis will be disproven if the x-squared obtained value is higher than this, as we are performing a one-tailed test.
Step 4. Computing the test statistic. In this step, we use the chart we had previously created to gain the x-squared obtained value. Although this was already completed in the fifth column of the computational table, there is a formula that goes along with it. The formula is x squared obtained is equal to the sum of f obtained minus f expected squared over the f expected. For our test, the x obtained is 2.88.
Step 5. Making a decision and interpreting the results of the test. This is the most important step as it allows us to decipher what the test is really telling us and is where the null hypothesis is either accepted or rejected. Due to the fact that the x squared obtained value of 2.88 is lower than the x squared critical value of 3.81, we cannot reject our null hypothesis as it is more likely than not that criminal victimization is independent from visible minority status. Unfortunately, the chi-square test does not give enough information on the degree of relation between the variables. It simply tells us whether or not there is a relationship.
To gain better insight into the relationship and compare the values in the bivariate table, column percentages can be calculated to see how the independent variable affects the dependent variable. Column percentages are defined as percentages computed within each column of the bivariate table. To calculate these, we divide the cell frequency by the total number of cases in that column, and then multiply by 100 to gain a percentage value. This is completed for each cell. The percentages for each column should equal 100%. To calculate the total percentage for each row, we take the cell frequency for both cells in the row, add them together and divide them by n, then multiply by 100 to gain the total percentage. This is repeated for both rows. We now see that the non-visible minorities are more likely to be victimized by crime, as 63.19% of non-visible minority status have been victimized by crime, whereas 56.47% of visible minorities were victims.
For SPSS, first you open the 2009 General Social Survey, click Analyze Descriptive Statistics, crosstabs, and then we want to change our variables to display variable names. We choose our two variables, which are life-fic for columns, and then our dependent variable goes in rows, which is minority status. You click statistics and we want the chi-square and then continue, and then we click on cells and we want expected as well as observed, continue, and then OK. This will produce 3 charts showing our data.
Thank you, come again.